By now, you are well aware of how growth hormone increases protein deposition and helps in the growth of almost all the tissues in the body. One important concept that we are left with is the skeletal growth. Yes, the growth hormone stimulates the growth of bones and cartilage in a very obvious manner. Well, the bones are composed of an organic matrix made up of the structural protein collagen, that is, combined with glycoproteins that forms a framework, within which the mineral hydroxyapatite is deposited. Now, there are two main varieties of bone structure. One of them is cortical, or compact bone. It has a dense structure, forming about 80% of bone in the body, and provides most of the strength of the skeleton. It forms the outer layer of all bones, and is particularly prevalent in the diaphysis, or shafts of limb bones. The other one is the trabecular, cancellous, or spongy bone, that has a more open structure than cortical bone, and surrounds the red bone marrow, and forms 20% of bone in the body. Well, the axial bones, such as the vertebrae, and the ends or epiphyses of long bones are largely composed of trabecular matrix. Now, in development, bones grow from the interface between the epiphysis and the diaphysis, that is known as the growth plate, epiphyseal plate, or epiphyseal cartilage. What happens is that, in response to the growth hormone stimulation, the long bones grow in length at this epiphyseal cartilage, where the epiphyses, or the ends of the bone, are separated from the shaft, or the diaphysis. This growth first causes deposition of new cartilage by rapidly dividing chondrocytes, that are cartilage-forming cells. Then, bone-forming cells, the osteoblasts, bring about the calcification of this cartilage, and hence, it is converted into new bone, thus elongating the shaft and pushing the epiphyses farther and farther apart. In this process, the growth plate is progressively used up. So, at about 20 years of age, the growth plate is all used up, and we do not have it left for the further growth in bone length. So, the bone elongation is stopped here. At this time, bony fusion occurs between the shaft and the epiphysis at each end. So, no further lengthening of the long bone can occur. This stage is known as epiphyseal closure. It is a process driven by the high levels of sex steroids present at puberty. Well, the osteoblasts, the bone-forming cells, deposit new bone on the surfaces of older bone, while the other bone cells, that are osteoclasts, remove old bone, or what we call resorption of bone. Now, when the rate of deposition is greater than that of resorption, obviously, the thickness of the bone increases, and growth hormone, strongly stimulates osteoblasts. Therefore, the bones can continue to become thicker throughout life. This is especially true for the membranous bones, like the jaw bones and the bones of skull can grow in thickness throughout the life. Well, the mature osteoblast also develop into osteocytes, that are another type of bone cells that have many processes that settle into spaces in the bone matrix and maintain its integrity. They can also secrete acids that dissolve hydroxyapatite, and thus provide free calcium to the circulation when required. The systemic insulin-like growth factor 1, IGF-1, and locally produced IGF-1 and IGF-2 stimulate the division, differentiation, and matrix-secreting activity of osteoblasts and chondrocytes, whereas members of the transforming growth factor beta, or TGAF beta family of growth factors, are thought to provide the same stimuli for osteoclasts. Well, the osteocytes, osteoclasts, and osteoblasts, all of these bone cells are present in mature bone, remodeling the bones throughout the life, and help in repair of fractured bones. Here, we are done with the effects of growth hormone on the bones. Now, let's see what happens in the case of hyper or hyposecretion of the growth hormone.
Explore our extensive library of over 1,800 video lectures to learn about a wide range of topics. Only on sqadia.com.